In this video, I'm going to show you how to do a multiple linear regression in Stata. If you want to follow along, I've got this data set here. You'll see the link to it down in the show notes. In this data set, I've got these various scale, meaning Likert scale type items, the sum of the scale items, race, which is 3 levels, age, gender, and another score. And these particular variables are fictional. This is a fictional data set. So the basics of running regression in Stata is the regress command. And we always put the y variable first. I'm going to use this sum scale variable. And then after that, I can list my my independent variables. Let's say I want to use age and race. Now, it's a little bit problematic to just list them because it thinks that race is a interval ratio or continuous type variable. And race has been coded as 1, 2, 3, representing 3 races, and it thinks that that's interval ratio, and so it doesn't give me quite the results I want. Well, let me show you how to get around that. If you have a variable that's categorical, then what you want to do is you want to, generally you would do some kind of dummy coding and compare all the levels of that one variable to some baseline. So let's suppose that I've got groups 1, 2, and 3, and I want to compare group 2 to group 1 and group 3 to group 1. In that particular case, what I do is I just put an I dot in front of that. An I dot means that it needs to create indicators, I for indicator. And what it's going to do is by default, if you just do an I dot, it's going to compare to the first group. So if I have 1, 2, and 3, or I've coded my 3 race groups here, it's going to compare each group to group 1. So I'll just hit enter. You see that I've got a coefficient for age, which was interval ratio, and then group 2 is compared to group 1, group 3 is compared to group 1, and you'll see it puts the interceptor constant last. It has all the typical statistics up here. I've got my R-scores, adjusted R-scores, which is actually negative, which is impossible, but it's got that because this is fictional data, so it's not fitting well. And then it has all the typical p-values here in this particular column, and so forth. And now I can play with that comparison here. Let's suppose that I wanted to compare to a different group instead of group 1. Again, this I dot tells you by default that it's going to compare to the lowest value. Well, then I use this more advanced command. I do IB. In parentheses, I'm going to tell it what group I want to compare to. Let's say I want to compare to group 2. And then I just do dot race. Okay, so IB in parentheses the group I want to be the baseline group that the others are compared to, and so forth. And I hit enter, and now you'll see that it's got the 2's missing here. The 1 is compared to the 2's, and the 3's are compared to the 2's. So you see that happens here. So there's a variety of things I can put where I put this to. I can put any of the values, the coded values, in this case a 1, 2, or a 3 in there. I can put first, which is again what we get by default. I can put last, which will give me the last group, group 3. I can put frequent. Now if I put frequent in there, it's going to make the baseline group the group that's the largest. So I have any of those options here by default, and it's usually, I find, just easiest to put in the group number that I want to do the comparison to. All right, that's the real basics of a multiple linear regression without interactions. We'll talk about interactions in just a minute. Before we do that, I want to go through how to do the diagnostics. When we're looking at diagnostics, we're looking at a variety of assumption violations. We're also looking for potential outliers. One of the easiest things to do is just this has to be after you've run your regression, type in RVF plot. It stands for residual versus fitted plot, or residual versus predicted values plot, which is very commonly used to look at assumptions. And what you see is this, when this pops open, we can look at a variety of things. First, I can look for extreme potential outliers, and I don't have any here. Okay. I can look for violations of linearity assumptions. If there's a curve to this, then I would be concerned that maybe I've got a violation to the linearity assumption, and I need to have some higher order term or some transformation of one or more of the variables in the model. That's something that I can look for. And I can also look for heteroskedasticity, which is when the model is fitting closer to the line at one end of the line than the other. In this case, it's not really a line, it's a plane or something higher order that's a similar analogous to a line but at higher dimensions. And you'll see that it's fitting. And if that were the case, you'd see that the points are closer at one end and wider at the other. So I'd get a triangular shape or funnel shape with one end of this having the points closer to this center 0 than at the other end. What it's basically telling me is that my smaller fitted values are associated with smaller residuals or vice versa. So that's something that can be if that happens, then you often need to do a transformation of the data as well, and often a log transformation of the y variable will solve that, but then interpretation becomes more complex. It's beyond this video. You might get the help of a statistician or look to see if later I had a video on that. So that's the things that I'm looking for here, those three things. I'm looking for extreme obvious outliers, I'm looking for obvious extreme curvilinearity, and I'm looking for heteroskedasticity, and I don't see any of those problems here. Okay, and we always want to do that after we run a regression. The other thing I like to look at is I like to look at a histogram or plot of the residuals. In order to do that, I need to create a variable that has the residuals in it. I'm going to use the predict command. So I just type predict, and then I'm going to give it a name of the name of my variable. I'm just call it res for residuals, comma r. Now there's a variety of things this predict command can create. If I were not to put it on there, if I didn't put the comma r, it would actually create predicted values instead of residuals. If I put the comma r, it creates residuals. So again, if I just take that off, I would actually be creating the predicted values for this based on this regression. So here I want residuals, so I'm going to add that option, hit enter, and you'll see in the data set that that's added down there. And then I can look at a histogram of those residuals, and I'm looking for any extreme obvious deviations from normality. So in this particular, I'm looking for extreme skewness. This is a teeny bit skewed. I want extreme skewness. And again, if I have extreme skewness, I may want to do some transformation of the data. Often a transformation of the y variable can fix that often. Not always, but that's the most common thing that would be a solution, to take a logarithm of one of the variables, and most often the y variable. So that's our look at assumptions here. So we're pretty good, okay, as far as those basic. Now some statisticians will recommend looking at other things, other kinds of plots or statistics. These are the ones that I think are most useful to use out, and they're simple and straightforward to simply look at them graphically. I don't typically like statistical tests of violations of normality, because they can be over sensitive and misleading. So you need to be aware of what happens if you were to have lack of normality. In that particular case, what it basically means is these p-values will be off. Okay, these will not be accurate if you don't have normality. And as far as the things that you look at with the RVF plot, okay, if you've got heteroskedasticity, that thing, then you will also have a problem with the p-values being inaccurate. However, if you have an outlier that's extremely influential, in a smaller data set, that's more likely that it's going to be influential. Or if you have a situation where the data is really curved in a straight line, it basically means these coefficients are misleading. Okay, and you can, if it's curved, you can fit something better than a line, and if you've got an outlier, you may consider whether or not you ought to remove that, which can be a judgment call. Okay, so that's the basics there. Now what we're going to do is we're going to look at doing interactions. Okay, so I've got these variables down here to play with. Right now I'm going to do a regression of some scale, and I'm just going to use, to start off with, two of my categorical variables, so gender and race. Okay, and I'm going to tell it that both of these are indicator variables. Okay, now what I do if I want an interaction between them is I'm going to put this pound sign right there. You actually technically don't have to, because as soon as you put a variable into an interaction, Stata by default assumes that it is a categorical variable, and you'll have to tell it if it's not. Actually, I'll do that in a minute. So I went ahead and did that, run the regression, I get my results. Let me show you if I were to leave off the I dots. You'll see that it treats them as categorical in the interaction, but not within the main effects. Okay, so a little bit clumsy, but you would have to put them in as an I dot here for the main effects of those two variables. But when it comes to doing the interactions, it's going to already assume that those are categorical. Okay, now here's another shortcut. If instead of writing out those main effects, I put a double pound there, okay, so gender pound race, with or without the I dot, it won't matter. You see what I end up getting here is that same result that we had just prior. Now, if we have the double pound here, what it tells it to do is to find that interaction between those terms and any lower effects. So if this is a two-way interaction, which it is, it's just two variables, then it will also find the main effects. Okay, so if I have it like this again, and I have the double pound sign there, it's going to tell me to find the interactions, and it's going to tell me to find those main effects, and it treats everything as categorical by default. Okay, if I were to type it this way, gender pound race, without the double pound and without putting gender and race in individually, it only gives me the interactions, no main effects, which is generally not reasonable. It's generally not something you want to do. So I'm going to put that back in there because it bothers me to have on the screen something you shouldn't do. So that's the basics of running doing interactions when they're all categorical. And to do a three-way interaction, you would just do a pound and then put the other name of the other variable here. I don't have another one, but if you had another one, you would type it like that. And by doing this double pound, it gives you the three-way interaction. It gives you all two-way interactions, and it gives you the main effects as well. Okay. If I could just put a single pound between each of those, it would only give me a three-way interaction, nothing else. Now, let's suppose that you wanted to include a continuous variable. I'm not going to do centering quite yet. I'll come back to that. So my other variable I've got here is age. Let's say I want to see if there's an interaction between age and race. Okay, now this is going to give me the main effects. It's also giving me the interactions. But look what happens when I hit that. It treated age as if it were a categorical variable. So every single age that is in the data set is treated as a different category. That's problematic. By default, again, within an interaction, it thinks it's categorical. I put a C dot in front of it, which stands for continuous in this particular case, meaning scale or interval ratio. Okay, so if I put a C dot in front of a variable, it forces it now to be continuous, or basically interval ratio, when the model is run, and I hit enter. So you see now it gives me age treated as a continuous variable, gives me race treated as categorical, and it gives me the interaction between those two with age treated as continuous and race treated as categorical. Because again, now this is an inconsistency, is when I have a variable listed without the pound signs, it's not included in any kind of an interaction, by default it thinks it's continuous. As soon as I put it in an interaction, and so in this particular case I have to do the I dot on race, or I can do the more complicated, say I wanted to use group 2 as my default group. Okay, this will do this correctly, main effects only, no interactions. As soon as I'm looking at interactions, the reverse is the case. And it's going to, if I were to put in there, put these both in interactions, now it assumes automatically both of them are categorical and will by default compare to the first group. So I've got to do that one as a C dot. If I want this race, a different group than the first group to be considered as my baseline, then I would do something like that. Okay, whoops. I forgot to put the dot in there. Okay, so now it's giving me exactly what I want. Age treated as continuous, or interval ratio is a better term. The race treated as categorical with group 2 as the baseline group, and then I have the interactions down here. So that's giving me all the things that I want there. Okay. Now let me just address one other issue. You may be aware that when we look at continuous variables in interactions, we often want to center them. Part of the reason has to do with interpretability, that essentially when I try to interpret an interaction, it's looking at, the difference between, in this case, group 1 and group 2 on the race had a baseline age of 0, which doesn't make any sense because nobody's age is 0. So what we often want to do is we want to center our continuous variables, which basically means subtract the mean from each of the age variables. It's fairly straightforward to do. We're just going to create a new variable. We're going to generate a new variable, and it's going to be, I'm going to call it centered age, like this, equals age minus our mean. Okay, so it's going to find the mean, okay, age, and it's going to center that. We hit enter, and you should see down here a new variable. We can look at it if we're worried about whether we did it right. It's not showing. Oh, it's all missing values because I did that not quite accurately. Apologize briefly over that. We need to do it this way. What you want to do is just do summary statistics for the age variable. And then what we can do is generate a new variable. I'm going to call it center age. Okay, equals. And then what I'm going to do is take age minus, and then I'm going to do our mean. What that does is it takes from the results up here the mean. And so I don't have to type in. Of course, I could just do age minus 29.94872. I could type that in there if I wanted to, but it's a little bit easier to do it this way, just to type in our mean, and that will create that variable that's centered by age. If you wanted to standardize a variable, it would be very similar. You would type in, just for the, since we're looking at right now, I'm going to do standard age equals age, parentheses age, minus our mean, and the whole thing would be over our SD for standard deviation to create that variable. If I wanted to standardize a variable, it would be the same idea. But in this case, we're just going to use the centered mean, and then I can go back and I can do my regression, and I can do my sum scale, and then I'm going to put in my variables. Let's say I'm going to do centered, age, and I've got to do a C dot in front of it to tell it that that is continuous. Okay, and then I'm going to do a double pound with race. Maybe for fun I'll do a double pound also with gender. And because I've done it that way, I'll pop it over here so you can see the command again. It's going to give me the three-way interaction. It's going to give me all two-way interactions. And it's going to give me the main effects. By default, it treats race and gender as categorical, using the first group as the, that one coded the lowest as the baseline, and it's going to treat this centered age as continuous or interval ratio because of the C dot in front of it. And you can see here, this is the three-way interaction down here. I've got my one-way interactions, all my different one-way actions, and I've got my, here's one main effect and my other main effects. So it's got everything included in there. And once I'm done with all that, I can type in RVF plot again to make sure that there's no severe, obvious, extreme outliers that might be biasing the results. I don't have any heteroscedasticity, and I don't have any curvilinearity, so I'm not going to worry about that. And I can create a predicted variable. I'll call it residual 1 since I already have a res. And I'm going to then create a histogram of that. When I'm done, make sure that it's not extreme, obvious skewness, some extreme deviation from normality in any way that would bias or change my p-values themselves. So that's an overview of how to do the basics of multiple linear regression here in Stata.